Hello everyone, welcome back to another GIS Mathematics lecture video. And in this lecture video, I want to continue our discussion on the transverse cylindrical projection by talking through how we take this alpha and this theta p, or the latitude of this p point that we have no idea what it is. Right, how we take those values and we use them to actually generate what we would want, which is an easting and a northing of our target point A here. And so what I want to do in this video is I want to walk through two different sets of equations. The first is an equidistant equation. And the second is what we would call a conformal equation. Now this conformal equation, this is actually the basis for UTM, or Universal Transverse Mercator. Now the UTM is a little bit different because it deals with an ellipsoid rather than a spheroid, so it's a little more complicated. But we're actually going to focus on just the spherical version. But again, it's a good building block to getting into the mathematics behind UTM. So let's go ahead and talk about the equidistant equation. So the equidistant equation is actually pretty straightforward. Our easting, right, so this is how far east or west we are. So if we go back up here to our diagram, right, our easting, right, how far east or west we are, looks like it would be related to this alpha. And that's actually exactly what it is, right? It's the radius of our reference globe times alpha. Let's draw a slightly better alpha here. Right, that's it. It's just like how with our normal projections, right, we had the easting was the radius times longitude. Well, in this case, our longitude is being replaced by this alpha here that we calculated, that we showed through the previous video. The northing, right, this is going to look very similar to the equidistant equation that we had for the normal, but instead of having it be the latitude of A that we use, we're actually going to use this latitude of P that we calculated, or had the example equation for in the previous video. So for the equidistant, right, instead of having it be based on the latitude of A, it's going to be based on the latitude of P. Right, so it's going to be based on this angle here. Right, this is the latitude of P. That's theta P. Now, I should make clear here, theta P does not equal theta A. I should make that clear. Theta P is its own different latitude related to the latitude of A, but it is not equal to it. Okay, so equidistant equation looks very similar to the equidistant equation for normal. We just replace latitude and longitude with this alpha and the latitude of P. Conformal, again, this is going to look pretty similar to the conformal equation before. Our easting is going to look our northing, in this case, is going to look identical. Right, it's going to be rho theta P, the radius of our reference globe times the latitude of P. And then hopefully I've left myself enough room here. Our easting is actually going to be the thing that we mess with. It's going to be equal to R times the natural log of the secant of alpha plus the tangent of alpha. Okay. R times the natural log of the secant of alpha plus the tangent of alpha. So again, I know we're just kind of putting down these equations here, but hopefully you see how these are related to these and how these are related to our reference globe and developable surface that we drew. If you have any questions, please reach out. And in the next video, we're going to go through a couple of examples of actually using these equations to calculate eastings and northings. So hopefully that makes sense. And as always, please reach out. Thank you.